Okay, class, so this is something that we didn't get a chance to talk about this week. It was something that I talked about, or that I wanted to talk about in lecture on Monday, and we didn't get a chance there, and then just lab was so busy this week. So I wanted to go through these slides. It's kind of in the middle of our lecture. This is something we haven't gone over, but it was something that we would have talked about before hybridization. So if you're following along, you can find the slide that says bond lengths on it, and we're going to kind of run through what these mean here. We talked about bond length. Bond length is like the distance between two nuclei, like this. We talked about how bond length gets bigger as things go down a column in the periodic table. And that was one of our kind of periodic trends, atomic radii, and how it influences bond length. Okay, so now I want to talk about how the number of electrons between atoms influences bond length. We can see on this end we have a triple bond, that's 6 electrons between the carbons. Here on this end we have a single bond, that's 2 electrons between the carbons. And we can see there's a big difference in their bond lengths. When you only have 2 electrons between the carbons, the bond is a lot longer, 154 picometers. And when you have 6 electrons, like here, it's 120 picometers. So it's not like it's 3 times less, but it is significantly smaller. And that's because the number of electrons pulls the atoms closer together. So if there's more electrons between them, the atoms themselves are pulled close together. And this trend is true whether we have homonuclear molecules or a homonuclear bond, which is when you have a carbon and a carbon or 2 of the same atoms bonded together. It's also true if you have a heteronuclear bond, which is when you have one atom and a different type of atom bonded to it. So here the trend is the same. As you get less and less electrons, the bonds get longer and longer, and that's because I kind of think of it as glue, like the electrons are glue between the atoms, and the electrons are kind of pulling the atoms together. So the less glue you have, the longer the bonds are going to be, and kind of the looser they are. Okay. And I just want to kind of point out something. These numbers that I have on the screen, so these picometer bond lengths, those are numbers that I looked up in our book. Those are numbers that we're going to calculate, or that we're really going to learn to calculate right now. So it's not like you're going to memorize these. We just want to know that the trend is that the more electrons and the more bonds you have between atoms, the shorter the bond length is. Okay, I changed this slide up from what you guys kind of are seeing. The text part was on, so the text part here was on the slide before. I needed to change it up because I needed us to have access to a periodic table so I can kind of show you this. What I've done here is I've cut out the P block from our periodic table just to kind of show some examples here. So one thing we talked about in the periodic trends in chapter 8 is that as you move across the periodic table in this direction, atoms are getting smaller. So these are the larger atoms, and these are the smaller atoms over here. And this influences our bond lengths because the size of the atoms influences bond length. Okay, so I want to look at how the periodic trends kind of influence our bond lengths here. So I'm going to look at this trend here. All right, the first one, so I'm going to be kind of looking down at our periodic table. The first one is a carbon to a carbon bond, and that's 154 picometers. The next one is a carbon to a nitrogen bond, and that's 147 picometers. The reason why the carbon-nitrogen bond is smaller is because nitrogens are smaller than carbons, and so as you get further away from the carbons going in this direction, the atoms are getting smaller, and you can see up here that the bond lengths are also getting smaller or getting shorter. And it isn't a crazy, like it isn't super drastic, but it is definitely a trend. Okay, now I want to look at our second trend here, this here. And this one was kind of mentioned before. We're talking about atoms as you go down a column. So we're going down the column here. As you go down a column, we see that atoms are smaller at the top, and bigger at the bottom. So that's one of our chapter 8 periodic trends. And so if you bond two fluorines together, so two fluorines together, those are going to be the shortest bond length because the atoms are smaller. And then as you go down, two bromines together would be bigger because each bromine atom itself is bigger. Okay, and we're going to start doing some math with this stuff. So we kind of need to relate these bond lengths to energies. And so I want to talk about this statement here. In general, as bonds get longer, they also get weaker. What that's saying there is that long bonds are easy to break. And so longer equals easier to break. And we also say that that is lower energy. The shorter and stronger a bond is, it's harder to break, and it has a higher bond energy. When we talk about the energy of a bond, we usually call them just bond energies. Okay. And that is the amount of energy that is needed to break a bond. If the bond is really strong, the bond energy is going to be high. If the bond is weak, the bond energy is going to be low. It's going to be easy to break that bond. And one way we can use those bond energies, so we can use bond energies to find the delta H of a reaction. That's something that we did back in chapter 6. We found the delta H of a reaction using a bunch of different ways. We used calorimeters, we used Hess's law. You guys got to think back to 3A. It was kind of at the end there. I know you guys were tired, but we did do a lot of stuff with delta H's of a reaction, and we found that there were multiple methods for finding the delta H of a reaction. This is going to be our next one, and probably not the last way that we can calculate delta H of a reaction, but this is a pretty useful one when we start relating it to our Lewis dot structures, which is what we're going to do next. So the delta H of a reaction can be calculated by comparing the cost of breaking bonds to the profit from making new bonds. And what we're saying there is it's going to cost some energy to break the reactants apart, but we're going to get back a lot of energy when we make products. And so we're going to kind of look at the cost and the profit from each one of these. And to do that, we're going to need to be able to look up bond energies. The ones that I'm going to be using in the next slides are from page 412 in the Tro book. Okay. You can also find them online, but anyways, if you're looking for my exact numbers, that's where I got mine. So you'll see some numbers come up in the next couple slides. They're not numbers that you would memorize. They're numbers that you would look up in a book. Okay, so we've said some things like the stronger the bond, are higher energy. When we say that, we're saying that they are hard to break. And I took the same bonds that we were looking at here, and what I did is I just looked up their bond energies. So a triple bond between carbons is 837 kilojoules. A single bond is, a little bit more than a third of that, but much lower energy than a triple bond. And this is the same trend that we were talking about before, where as the bond length gets longer, so these are longer bonds. Oops. So these are longer bonds here. They are weaker, and they are lower energy. Sorry, that's getting a little messy. All right, and here it says the shorter the covalent bond, the stronger the bond. And when we are relating it to this trend right here, okay, the bromine fluorine is the shortest, out of all these. The bromine-bromine is the longest. That's because fluorines are so much smaller than bromines that their bond length is much shorter, and so they have a higher energy. So the shorter the covalent bond, the stronger the covalent bond. So I'd like to start doing some problems with these numbers, and so we're going to use the average bond energies to estimate the delta H of a reaction. Now there's some things about this. It works best when the reactants and products are in the gaseous state, like the estimation is best, but it's a good estimation no matter what. And some things that we have to think about when we're talking about the delta H of a reaction is something that I kind of start with something I said before, that when we break bonds, it requires energy, so we call that endothermic, so this takes energy. And anytime we have to put energy into a reaction, the delta H is positive. When we make products, so when we make bonds, it's exothermic. That means that we get back energy. And anytime we get energy back, the delta H is negative. So the delta H that we're going to put in for any bonds that we make are going to have a negative sign in front of them. Now the equation that we use to put these two things together is right down here. Okay. And what this is saying is that the delta H of the reaction is equal to the amount of energy that it takes to break the bond. So that's kind of our investment of energy. And then we also have to take into consideration how much energy we're going to get back when the bonds are formed. So this is the amount of energy that we get back. And the reason why there's a positive sign here, that seems a little bit weird because you're adding these two numbers together when really we should be looking at the difference between them. But anytime that we make bonds, their energy is going to be negative. So there's going to be a negative sign out in front of these. And so even though there's a positive here, all the numbers on this side are going to be negative. So I know the equation has a positive, but because it's an exothermic process, we're going to have to make these numbers negative. And I'll kind of show you how to do that when we get to the problem. Okay, this is kind of a visual way of looking at these problems. What we're doing here is we're starting with our reactants. And the first thing that we have to do is we have to break them apart. So we're trying to get from this methane molecule and the chlorine gas, so the chlorine gas here, and what we're trying to do is we're trying to react them. And what's going to happen is one of the chlorines is going to go like on to the carbon, and that means that it has to break one of these bonds. So the first thing that we need to do is we need to break a carbon-hydrogen bond, and we need to break apart the chlorine-chlorine. That's an investment of energy. So it takes energy to do that. So we're kind of going up in our energy scale here. Once we've reached this top, we have broken off that hydrogen from the carbon that we had before, and we broke these guys from each other. Now, once the chlorine goes onto that carbon, we're making a bond, and we get energy back when that happens. So we're going to go down. So this is how much energy we get back. All right, so this is like our investment. This is the profit. And the delta H of the reaction is the difference between them. Okay. So the more profit we get back, the more difference there's gonna be. Okay, and these are our reactants over here. Okay, so now I kind of want to put these numbers together. What we're going to do is we are going to look at a reaction, and we are going to look at the bonds. We are going to find the bond energies, and we're going to use that information to find the delta H of a reaction. The reaction that I want to do is, or the example that I want to do is hydrogen gas plus oxygen gas going to make hydrogen peroxide gas. And the first thing that we need to do is we are going to draw Lewis structures for each of the products and reactants. Okay, so I'm hoping none of these are too challenging for you. This is a hydrogen, so that's an H2. The O2 is, let's see, valence electrons is 12. So when I do that, I came out with a double bond like this. And that's the only way that I could get 12 valence electrons in there and everything have an octet. And then we are making hydrogen peroxide. That's ugly. So hydrogen peroxide, it looks like this. Very symmetrical. Like that. Okay. So if you need to pause here and kind of work through those to make sure that I am doing those right, and that you kind of agree, this is a good place to pause to kind of practice your Lewis structures. But I'm going to go on from here. The next thing that we're going to do is we are going to look at bonds that need to be broken and bonds that need to be made. And we're going to do a little accounting. So on this side, I'm going to look at the bonds that I need to break. And on this side, I'm going to look at the bonds that I need to make. I'm going to draw a little line in between this. Okay. On the reactant side, I need to break a hydrogen-hydrogen bond. And I also need to break an oxygen-oxygen double bond. There's usually two listings for oxygen-oxygen double bonds. It's because an oxygen-oxygen double bond that is just in an O2 molecule is different than when that's within a molecule. So we just need to make sure that we look up the right number there. But that's what I need to break. When I looked on page 412 for the energies, I saw that hydrogen-hydrogen bonds, so this guy right here, it takes 436 kilojoules to break 1 mole of that. And if it sounds funny that I'm saying mole, I just want to remind you that we don't write the coefficients of 1 out in front here, but there is a 1 kind of technically. So I'm breaking 1 mole of hydrogen apart. And so this is 436 kilojoules per mole. But there's just 1 mole, so that's not going to change our math. For the oxygen-oxygen double bond in an oxygen gas, it was 496 per mole. Okay, so when I add those up, it was 932 total. And the reason why I'm making sure I put that plus there is because we are investing this energy. It's endothermic. That number is a positive number. It's our kilojoules. On the making side, I need to make a hydrogen-oxygen bond and another hydrogen-oxygen bond, so 2 hydrogen-oxygen bonds. I looked those up. They are 463 kilojoules per mole, and I have 2 moles because I need 2 of them. I need this one and I need this one, so I need 2 of those. The other thing that I need to make is this bond here. It is a oxygen-oxygen bond, and that is 142 kilojoules per mole. I only have 1 of those. So the total is, on this side, negative 1068. Now that negative sign is important because I'm getting back this energy. It is exothermic. So that's why I knew to put the negative sign here. In the table, these guys here are listed as positive numbers. That's because the table doesn't know whether you're making the bonds or breaking the bonds. You get to decide what the sign is depending on what process you're doing there. But our making sign always needs to be negative. It always is exothermic. So the equation that we used is that the delta H of reaction is equal to the energy, so the sum of the energies of the bonds that are broken, plus the sum of the energies of the bonds that are made. And the way we do that here is delta H of the reaction equals 932 kilojoules. So that's our broken, the ones we're breaking. And then we are adding a negative 1068 kilojoules. Okay, we're kind of running out of a little room there, but the total is negative 136 kilojoules. And that's how we find the delta H of a reaction. So we're finding the delta H of a reaction by looking at a reaction, looking at the Lewis dot structures, and then finding off the bond energies. So I should have added some things to my list here. I didn't. Okay. So we drew Lewis structures. We looked at bonds that are being broken and made. We found bond energies. And we did broken energies plus the energy that we get back when we made it. Like that. Okay, so we used this reaction, or this equation right here. Okay, so in this kind of little mini lecture here, what we did is we looked at bond lengths, we looked at bond strengths, and we looked at bond energies, and we used that information to find the delta H of a reaction. In your book, so in the TRO book, this is chapter 9, and I think it's actually 9.10, that has the table and the calculations and things like that. So you're going to do some homework problems that are that have to do with this, and if you have any questions, feel free to ask them on Monday when we have our Zoom conference. I hope you guys are doing good, and hopefully I'll see you soon. Bye.